So now let's look at that theorem 17. Okay, that one is quite interesting also. Okay, it tells you that if you have a basis of E, so we still have this linear map that belongs to uh, the set of linear maps between some vector space E and some vector space F. Okay, so it says that if you've got a basis of E, then the image of F is actually spanned by the image of F is spanned by the images of the vectors of a basis of E. That's an interesting one, okay? So you should try to remember this kind of theorems to both ways, using so at the same time the math notation and understanding exactly what it means. Okay, all right. So that's interesting. Well, why do we have this? It's very simple, actually. We can say that what does it mean for a set to be spanned by some vectors? Of course, f of ei are a set of vectors. So we've got, it makes a family. Okay, it makes a family for I equals 1 to n if we have an n-dimensional space. Okay, so that's a family. And what does it mean to say that this is a spanning family? It means that for any y that belongs to the set I'm looking at, so in our case it's the image of F, can we find a linear combination of vectors of this family, so of F of EI, such that y is equal to this linear combination. So y is equal to lambda 0, lambda 1 f of E1 plus lambda 2 f of E2, etc., f plus lambda n f of En. Okay, can we find for any element y in that vector space, because we just proved that it was a vector space, that it can be expressed as a linear combination of f of ei. Okay, so actually, yes, it's, as I said, it's very simple. You just have to say that y belongs to the image of f. What does it mean? It just means that there exists some x in E such that f of x is equal to y. That's what it means, that we have an element of the image of f. Okay, but if that x, again, let's go on interpreting what it means. X belongs to E, it means that it can be expressed as x1 e1 plus x2 e2 plus blah blah plus xn en, okay, as e1 up to en is a basis of E. And it even means that this linear combination is unique, okay? As it is a basis, it means it's unique. If we didn't know it were unique, we would have only a spanning set, but as it's a basis, we know it's unique. Okay, good. So what does it mean then to take the image of f of x? What does it mean? It means that I'm doing f of x1 e1 plus x2 e2 plus xn en. So maybe something that was not clear enough. When I'm writing this linear combination, I have that x1 up to xn are the coordinates of x in the basis e1 up to en. Okay, so what I want to stress up here is that all the xk are real numbers. Okay, for k equals 1 to n, right? All the xk, this is a real number, that's a real number, etc. Okay, and This is a vector, this is a vector, this is, well, the equivalent of a vector, you know, that is going to span um, our set. Right, so when I write f of x, actually what I mean is f of x1 e1 plus x2 e2 plus xn en, because this linear combination is exactly equal to x. Using the linearity of f, what do we get? We get that it's x1 f of e1 plus x2 f of e2 plus xn f of en. And this is it. As f of x is equal to y, we get that all the y's that belong to the image of f's, for which we can find some x such that f of x is equal to y, is actually going to be written as real number times image by f of e1 plus another real number image of f by f of e2, etc. For this is true for all the items of the basis. So real number times the image of an element of the basis. So that's it. We can conclude that f of e1, f of en is spanning image of f. Okay. I don't know, it may be a basis, but to prove that it's a basis, we would need to prove also that it's spanning, but it's also linearly independent, which, well, we don't have to have. Okay, this is we can really have a spanning family that is not going to be linearly independent. So I know it's spanning, but I don't know if it's a basis.